Hello everybody, Chapter 1, Lesson E, Part 1 on combining functions. Our objectives for the day are to combine functions arithmetically using sum, difference, product, and quotient, and then to find the domains of functions combined using these methods. Let's go ahead and get started. Today's lesson is going to use some basic methods of arithmetic, addition, subtraction, multiplication, and division. And just as two numbers can be combined using these four basic operations, so can two functions be combined in the same way. An example, consider the following functions f of x and g of x. F of x is x plus 7, linear. G of x is x squared minus 3, quadratic. In part 1, I'm going to take f of x minus g of x. In doing so, f of x being x plus 7, and g of x being x squared minus 3. I have to be careful for some algebra here, but f of x minus g of x, written in a standard form, would be negative x squared plus x plus 10. Notice I get the plus 10 from 7 minus a negative 3. Okay, f of x plus g of x would be the same expressions, x plus 7 plus x squared minus 3. Using our skills with algebra and combining these like terms, the only like terms I see up here are 7 and negative 3. I'm going to get x squared plus x plus 4. Two very different functions just by adding and subtracting. Okay, f of x times g of x. We're going to have to use some of our skills with the method called foiling. I'm sure that method you recall. Maybe need a little refresher here, which we can definitely do. I'm going to take the first terms for f, which is FOIL. That would be x times x squared, which is x cubed. Then outside, x times negative 3, that's a negative 3x. Then inside, that's the I in FOIL, which would be 7x squared. And then last, oops, that was not last. Last would be from 7 to negative 3, which is a negative 21. Now if I were to put this in standard form, it would be x cubed plus 7x squared minus 3x minus 21. Excellent. F of x divided by g of x. Well, f of x divided by g of x in this case is x plus 7 over x squared minus 3. We would be complete there. There's nothing more to simplify. A note here at the bottom, the domain of an arithmetic combination of functions consists of all real numbers that are common to the domain of those functions. We're going to do an example of that in just a moment on the next slide. So here we have example 1, using f of x and g of x. Answer and evaluate the following. F of x is linear, g of x is a quadratic. I'm going to find f of x divided by g of x. Now it's a slightly different form than what we saw on the last page. This is still the same thing as f of x divided by g of x. Okay, that's equivalent forms. So f divided by g of x is 2x plus 1 over x squared plus 2x plus 1. G divided by f of x is just the reciprocal of that. X squared plus 2x plus 1 over 2x plus 1. Okay, let's determine the domain of f divided by g of x. Notice that f's domain would be all real numbers, and so would g's domain would be all real numbers. However, when we divide them, let's take f of x divided by g of x first, we do not want the denominator to equal 0. So the domain of f divided by g is going to be anything that makes the denominator 0. Let's do some algebra on that. X squared plus 2x plus 1. We don't want to equal 0. So what I want to do is find out where it equals 0. So I factor. That would be an x plus a 1 and another x plus a 1. So it looks like the only place where I could get 0 is when x equals -1. That would make one of those two factors equal 0. Therefore, that would be an issue. Therefore, the domain would be everything not equal to -1. We could again write that in our interval notation using the following. Obviously, in this case, this notation would be preferable. Likewise, for the domain of g of f, or g divided by f, I'm going to look at this function here. And again, I want the denominator. I want to know where it equals 0. And I don't like that value because then we're going to have a 0 in the denominator, which causes our calculator to explode. It looks like if I subtract 1 and divide by 2, I get a -1/2. Again, domain here, x is not equal to -1/2. Outstanding. I'm not going to write that in interval notation. You could do that. So let's find f divided by g of 3. So if I take f divided by g and I plug in a 3, I'm going to get 2 times 3 plus 1 over 3 squared plus 2 times 3 plus 1. That's going to come out to be 7 over 9 plus 7, which is 16. So f divided by g of 3 is equal to 7/16. How about g divided by f of 7? That would be 7 squared plus 2 times 7 plus 1 divided by 2 times 7 plus 1. Well, that would be 49. I'm going to do the numerator here first, plus 15 over 15. 49 and 15 would be a 64 over 15. That is not reducible. Therefore, I would be complete right there. Awesome. Let's keep moving. That would be a combination through division. Let's go on to example 2. Let's combine these functions f of x and g of x using what looks like a product. So f of x is x squared, g of x is x minus 3. So in order to get f times g of x, I'm going to multiply x squared times x minus 3. Don't forget that we are going to distribute to both terms. So f times g of x is equal to x cubed minus 3x squared. Okay, the domain. I don't have any rational function. I don't have any even root. Therefore, the domain of f times g is going to be all real numbers. Evaluate f times g of -5. That would be -5 cubed minus 3 times -5 squared. That's going to be -125 minus 75. When I square this negative, it becomes positive. Therefore, that negative stays there. And it looks like I'm going to get a -200. So that's f times g of -5. Awesome. Now, with products, it doesn't matter if I have f times g or g times f. Okay, with quotient, it does, as well as with sums and differences. So the product is kind of the nicest of the 4 arithmetic combinations in that if I switch the order in which I'm multiplying, it won't make a difference on the end result. Okay, let's go to the next example. Okay, here we go. F of x is 1 over x minus 5. G of x is the square root of x minus 3. I want to find f plus g of x. Well, this is kind of an interesting example in that there's nothing I can really do to combine these two functions. I mean, I could find a common denominator, but that would actually make this more complicated. So I'm just going to leave it right like that. So f plus g of x is 1 over x minus 5 plus square root of x minus 3. Now, if I want the domain of this function, this is really interesting. Both bring restrictions. Okay, the first expression, 1 over x minus 5, brings the restriction. So the domain of f is going to be x cannot equal 5. Okay, the second expression, the domain of g, is going to be related to the following. I want x minus 3 to be greater than or equal to 0. Therefore, I want x to be greater than or equal to 3. Now, if I want a new function with the combination of these two, then both of these things have to be satisfied. The domain of the first and the domain of the second. So if this new function has to be greater than or equal to 3 for its domain, but can't equal 5, then the domain of f plus g will have to be, I'm going to put it in interval notation here, 3 up to 5, unioned with 5 up to infinity. Union means in addition to. So there's this gap at 5. Therefore, that would account for all values greater than or equal to 3, not equaling 5. That'd be the domain of f plus g. So f plus g of 2. F plus g of 2 will be exactly what we have. That'd be 1 over 2 minus 5 plus the square root of 2 minus 3. Now notice what's going to happen here. I'm going to get a negative 1/3 plus the square root of negative 1. That can't happen. Notice that 2 is not in our domain. Not in our domain. So you have to be very careful. We cannot evaluate. Cannot evaluate. Therefore, f plus g of 2 does not exist. This is a universal symbol in math for does not exist. We cannot evaluate it because 2 is not in our domain. Very careful while you do these problems, just check to be sure that the input is in your domain. All right, let's move to the next question. I absolutely love these questions graphically, looking at f of x and g of x. Now, you could actually define f of x where I could say that f of x is, let's see here, this would be 2 absolute value of x minus 2, right? This is the absolute value of x. Now, if I were to sketch the absolute value of x, it would look like this. But notice that our vertex of our absolute value function has been shifted over 2 units. That's this value. And then the stems of the absolute value have been stretched by a factor of 2. Okay, that's cool. G of x is equal to 4 minus x. This is an equation of a line that has a y-intercept of 4 and a slope of negative 1. Now, these are not necessary. You do not have to look at the function and function notation. You can strictly look at the graph, and that's totally fine. So f plus g of 3 is the same as f of 3 plus g of 3. Okay, if I look at f of 3 is right here. Oops, I'm sorry. That's not at all where it is. F of 3 is here. It's 2. And g of 3 is 1. So f plus g of 3 is actually 3. F divided by g of 2 is f of 2 divided by g of 2. F of 2, if I look at the graph, is 0. G of 2 is 2. Therefore, f divided by g of 2 equals 0. F times g of 1 is the same as f of 1 times g of 1. F of 1 is 4. G of 1 is 4. Therefore, f times g of 1 is equal to 16. Okay, f minus g of x is the same as f of x minus g of x. Now that's where our equations come into play here. So we would have 2 times the absolute value of x minus 2 minus 4 minus x. So instead of minus 4 minus x, I'm going to say plus x minus 4. Okay, now note I gave you the general equation as a hint that you should look at what the function equations are. That's it's probably a little bit of a heavier idea or concept, and you won't always be able to find the equation of a function. In this case you can, but you can't always. If it were to be piecewise with a circle as part of it, and etc. So please don't focus too much on part 4 there, other than just get the basic concepts. Okay, so let's find the domain of g divided by f of x. Okay, so the domain of g divided by f of x. Well, this is interesting because we want to know, in this case, if we want the domain of g divided by f, I want to know where f of x equals 0, because if f of x equals 0, we've got issues. Therefore, it looks like f of x equals 0 at 2. Therefore, we can say that x cannot equal 2. If x equals 2, we're dividing by 0, and we got problems. Okay, guys, I got one last slide for you. It's a bonus slide, so if you're up for the challenge, go ahead and join me. Okay, so we got a square foundation that was prepared as a base for a cylindrical pool. So we got a circular pool on this concrete pad. Let's write the radius, r, of the tank as a function of the length of one of its sides. Okay, so let's relate the two of them. Notice we've got a square, and of course the definition of a radius is that it's half the distance across the pool, or half the diameter. And notice that the diameter would be the same as the side length of the concrete pad. Therefore, what I could say is that x equals 2r. Therefore, r as a function of x is that r equals x over 2. Okay, write the area, a of r, of the circular base of the pool as a function of the radius. All right, well, a of r is equal to pi r squared. I think I wanted to add a little bit more to this question because that's pretty basic. But what we could do is we could then write a as a function of x. So that would be pi times x over 2 squared. So the area of the circular pool with respect to x would be pi times x squared over 4. Okay, guys, these are good problems to be trying. I likely won't assess you on them, but later on this semester, toward the end of the semester, we'll be doing some word problems where this will show up. So I want you to start getting repetition, seeing this stuff. If you do nothing other than just listen to this problem and try to start to understand the process, that's the best thing you could do at this point. So hope you're well, and shoot me any questions if you got them. Thanks. See you in the next video.